Hello and welcome once again for another ES340 Engineering Thermodynamics video. This is day 5, part A. So we're going to start off with phases and pure substances, and we'll talk about non-pure substances as well in a moment. So when we talk about a phase, what we're really talking about is the state that the structure of the substance is in. So what is that? What do we mean by the state? Well, what I mean by the state is whether it's a solid, a liquid, or a vapor. There are now other accepted phases, but these are the common ones, and these are what we will be dealing with in the course. And when we say that something is pure, what we mean is that it is uniform in the sense that it's all in the same phase. So if we say pure solid, no mixture of solid with other phases, pure liquid, that would mean, again, no mixture of liquid with other phases, and so on, right? So when it's pure, there's no mixture of phases. Now, we can have cases that are not pure. And we'll see that. So we can have mixtures of phases. In fact, we can even have, in some circumstances, we can have, it's very special circumstances, but we can even have all three of those states mixed together. The triple point, where it's solid, liquid, and vapor all mixed together. But that, of course, takes very special pressures and temperatures and volumes. Now, one thing that we have to note is that not all properties are independent. In fact, we're going to be talking about intensive properties specifically. So there are intensive properties include things like the temperature, the pressure, and the specific volume. The specific internal energy is another example. Specific enthalpy is something that we'll see. So intensive properties include temperature, pressure, specific volume, specific internal energy, and specific enthalpy. We haven't talked about enthalpy yet, but we'll get there. These are examples of intensive properties. And what we're often going to be interested in is something called the intensive state. So the intensive state is something that can be described by the intensive properties of the system. So that's what we mean by not all properties are independent. And when I say that, I mean not all intensive properties are independent. In fact, in a special case that we call simple compressible systems, only two intensive states are required, let me rewrite that, to define the intensive state. Only two intensive properties, excuse me. I was using the wrong word there. The intensive state in a simple compressible system. Now, it's important to note that we're generally going to deal in this course with simple compressible systems, but not everything can be considered a simple compressible system. And in fact, you will probably encounter such systems that are not simple compressible in courses like fluid mechanics. But in this course, we will generally deal with the simple compressible systems, which means that all that we need to know are two intensive thermodynamic properties. Okay, so we only need to know, say, temperature and pressure as an example, and that will determine the entire state of the system just by knowing those two properties. Okay, so in a simple compressible system. So that's what we will be what we will be dealing with here. Now, in a simple compressible system, this is the reason why we like simple compressible systems. And again, this is just a simplification, right? This is not the real world, but in some cases, it's close enough. In a simple compressible system, work generally happens during quasi-static processes. So we can assume that we have an equilibrium at each state, right? When we have a quasi-static, it's also called quasi-equilibrium. We can assume that at each state, at each intermediate state, in between the start and the end of the process, we go through equilibrium points, right? So so that's the nice thing about simple compressible systems, and that makes computation much easier in such a system, as we'll see. Okay, so now we're going to talk about the PV-T relation. Oops, I meant to make a dash here. Where P is the pressure, of course, V is the specific volume, and T is the temperature. Your textbook uses like a lowercase v for specific volume, and I'll try to match that as best I can when I'm doing this. I actually make something that looks more like a mu, or a nu, I mean, but close enough. Okay, so again, remember that all we actually need are two intensive properties to fully define the state, because we're going to assume throughout most of the book, or maybe all of it, and if depending on how much time we have, we're going to be assuming that we're dealing with simple compressible systems. And so we only need two properties, but this is a plot of three properties against each other. And you can kind of see some details over here, like, for instance, when the pressure is low enough and the specific volume is small enough, we're in the solid range, right? And the temperature is small enough. Temperature's here, the specific volume is here, and then the pressure is here. So when these are kind of relatively small, well, even under high pressure, it stays solid, right? It just keeps going up. But when volume and temperature are relatively small, we're in the solid state, which makes sense, right? Because solids tend to be packed together much more than liquids or vapors. They're denser. So when you have a smaller volume and a small enough temperature, it's in the solid state. But then notice as the temperature rises, so as we go this way on this axis, as the temperature rises, we go through the solid liquid state, and then we get to the liquid state, and then we get to a point where we get into, depending on the volume, of course, we get into a vapor state, right? So increasing the temperature and allowing that specific volume to increase, eventually we hit a vapor phase. Okay, so this all kind of makes sense probably from experience. You could definitely think of like something like water, where if you cool it off enough, the temperature is low enough, it's solid, then you heat it up, it becomes liquid, then you heat it up more, it becomes vapor. But what we're going to really be interested in is not this triple diagram here, but we're going to be really interested in pairs of intensive properties. Because again, in a simple compressible system, that's all that we need are pairs of properties to entirely define the state. Now, I mentioned something here that is interesting. This is a pressure. This is called a PT. It has another name as well, but we're not going to go into that quite yet. But we have a PT diagram over here, and the PT diagram is nice because it shows something called the triple point on it. So the triple point is that exact place where all of those phases coexist. You can have solid, vapor, and liquid. Now notice if the temperature gets larger over here, again we get into the vapor phase. This critical point is kind of where things get separated out. So this is where you separate between, say, vapor and liquid. Over here, when the temperature is lower, we are in the solid, right? And now we also have to have a high enough, when we have a high pressure, notice that when we have a high pressure, even at higher temperatures, like over in here, we can still have a liquid, right? As pressure gets bigger, we can still have a liquid. You can imagine as if I carry this line through, you can still have a liquid over here, even as the temperature rises, because the pressure is enough to hold it together into a liquid form, okay? But low temperature and reasonable pressure, we have a solid, right? So this makes sense in the PT diagram. We're not going to deal a ton with it, but we will deal with the PT diagram. What we're really going to deal a lot with is the PV diagram, which is this one over here. So the pressure and the specific volume. Now, in this case, we also want to identify places where we have vapor, liquid, and whatnot. And furthermore, we should identify very special parts of this diagram. So this diagram over here, where I'm marking in red, I'm going to make it thick, right up to the triple point. If I'm on that line, not if I'm on either side of the line, but if I'm on that line, this is the saturated liquid line. This is going to be very important, so pay attention. That's the saturated liquid line. Over here that I'm marking in blue, just past that critical point, the critical point is where they coexist. This is the, excuse me, saturated vapor region. And then in between, let me just get a different color here so we can distinguish. In between this region and here is where it's a mixture of vapor and liquid. So it's a liquid vapor mixture. Okay, and furthermore, if I'm more to the left, I'm in this region. If I'm closer to the left side, I have a higher amount, a larger amount of saturated liquid. If I'm closer to the right-hand side, I have a larger amount of saturated of vapor, excuse me. And in the middle, of course, I have exactly equal liquid and vapor. Okay, so you have to keep that in mind. Now, over here is something interesting. Let me change the color again, maybe like a purple. Over in this region, on this side, if I'm off the line, and I'm going to make a little dash line at the critical point here. So if I'm off the line, and I'm on this left-hand side, this is called the compressed liquid region. And over here, let me change this color again, maybe get an orange. When I'm off the line, over here, again, past that dashed line there, I'm in the superheated vapor region. Okay, and again, that's off the line. On the line, saturated vapor, so that blue area, saturated vapor. But off the line, I'm in the superheated vapor region. Okay, so this is going to be very important that you familiarize yourself with this diagram, because we are going to use this as the course goes on. So I do suggest that you take notes about this and you come back to it later and make sure that you kind of understand what is going on there. So I discussed the saturation line and all of this good stuff. I should discuss what I mean by these things. So saturation temperature. This is the temperature at which a phase change takes place. So in other words, in this PV diagram, the saturation temperature would be the temperature that is that we start at when we get to that red line. However, during phase changes, this is important. The temperature remains constant. I want you to pound that into your head. Okay? And also that's true of the pressure. So as I go across this diagram, this PV diagram, the saturation temperature is constant. It's the same temperature from red all the way over to blue. Once I get off of that, then the temperature changes. the temperature changes in that case. Now, you can also say the same thing about saturation pressure. And it's the same idea as the temperature. It's the pressure at which a phase change takes place. Okay, so it's the same thing. And it also constant during phase changes. Okay, so that's important. But notice one thing, one very specific thing about this. So you might ask, what changes, right? Because typically during a phase change, you're adding heat. So you would expect something must change. And we can actually see exactly what it does on the PV, what does change on the PV diagram. Is that going from that red line to blue line, the temperature stays the same, the pressure stays the same, but the specific volume is increasing as we go from liquid to vapor, or decreasing when we go from vapor to liquid, right? So that is what actually changes here. Now we also have the TV diagram, and we will also use this one. In fact, we'll also use this one. This one might be the one we actually use the most. But the idea is the same. Notice that we have a liquid vapor here. Over here, again, it's the same idea. This side of the curve, it's actually exactly the same as the PV diagram. This side of the curve, we have a saturated liquid. This side of the curve, we have a saturated vapor. Over here, oops, that's not what I wanted. Over here we have superheated vapor. Over here we have, I keep forgetting to change it. Over here in this region we have the compressed liquid. And in between we have the mix. So it's just like the PV diagram. It's not the same as the PT diagram, but it is the same as the PV diagram. So it's a mixture in there, liquid vapor, okay? Again, this is going to be important. This one, obviously, we're going to use this a lot. This is going to be important for the purposes of this course. Now, these lines over here on the TV diagram, these lines right here are lines of constant pressure. So notice that TV has no pressure on it specifically, so we like to kind of show you how it would look in a 2D case versus a 3D case. And so without having to use the 3D case, this is how we kind of express it. So these are the constant pressure lines. These are also called isobars. Constant pressure curves, I guess, is the better word. Okay. Those are our isobars. And this is going to be a topic that we use over and over again, because this actually will tell you which table should I use. Should I use the compressed table? We're going to call them the steam tables. Should I use the compressed table? Should I use the superheated table? Should I use the saturated table, which would be anything on the curve or in between? Okay, so the mixture or saturated liquid, saturated vapor. Being able to identify things on here, where things go, is very important. So I want you to take time and learn this. That's all that I have for this video. I have another one coming soon.